Yeah, no, that would be perfect. Yeah,
Does it come on? Reach. Testing. Good morning. My name is Leonard Kahn. I'm chair of the physics department, and we're thrilled to welcome you to our Frontiers in Quantum Computing conference. We started planning this in the summer of 2019. Think back to the summer of 2019. We hadn't heard of COVID yet. It's been a long and winding road to get this program, this conference, to where it is. The conference is a celebration of the launch of our master's degree in quantum computing. And we hope that the discussions and the talks that you have here today and tomorrow and on Wednesday will be enlightening and enjoyable. I'd like to give some programming notes in advance. At 9:45 today, Senator Jack Reed will be joining us for some brief remarks. At noon, we will be going back over to the Welcome Center for a luncheon sponsored by D-Wave. Everybody with a lanyard gets free lunch, so make sure you hold on to your lanyards. By the way, these lanyards will get you into all the events afterwards without having to show your vaccination card. This evening in Beaupre Auditorium, which is just due north of here, as you head out in the evening, you'll see it. It looks like an ocean liner just past Chafee. And the speaker will be Umesh Vazirani, and he'll be giving the Alexander Cruikshank lecture. And he's going to touch on some of the philosophical implications of quantum computing. So it should be an interesting talk for people of all disciplines. I would like to take this time to thank our sponsors, D-Wave, IBM, Zapata Computing, PSSC Labs, and Microwave. Without sponsorship, without their support, this conference doesn't happen. I'd also like to acknowledge the steering committee, which is responsible for this conference. Vanita Srinivasa, professor of physics and director of the Quantum Information Science program. Gaurav Khanna, who is director of research computing and professor of physics. And Christopher Savoy, who is co-founder and CEO of Zapata Computing. I'd also like to acknowledge the support we've received, the generous support we received from the Office of the President, from the Provost's office, from university libraries, and from Information Technology Services. It's now my great pleasure to introduce Jen Riley. Without her support, our program and our conference would still be on the drawing boards. Jen? Thank you.
good morning, everyone. On behalf of the College of Arts and Sciences, welcome to the University of Rhode Island. We're really happy to have you here today. We're thrilled you've joined us. We have people here in person and virtually, and we're reaching close to 300 registrants for this conference, which speaks to the import and interest in quantum computing and technologies. Len gives me a lot of credit, but 3 years ago, the best thing I ever did was I convinced Len to become the chair of the physics department and take the helm. Since then, he has been a driving force behind our new quantum information science initiative in the department, which has led to this conference and our new master's program in quantum computing. Our program aligns closely with the strategic goals of the National Quantum Initiative Act as we seek to contribute to the expansion of the researchers, educators, and students working in this field. Through a multidisciplinary curriculum and various research opportunities, we hope to stimulate research in quantum-based technologies. We expect our program to become an essential contributor to the development of a workforce in the field of quantum information science as we work to maintain our country's competitive advantage in this arena, as well as help to ensure our national security. Some of the presentations you will see over the next few days stress how the education process in this area can and should begin before students reach college. We know we need to reach backwards into high school and middle school. As we all embark on this work, and I think we've all seen this particularly in the last few years, every effort must be made to be inclusive so that no groups are left behind in this second quantum revolution. Our physics department here at URI has always been in front on this issue. They have worked actively to engage underrepresented students early on before they reach URI, and they've also worked with our talent development program, including creating a new program for the students this summer to bridge them into the university more successfully. Further, we are partnering with industrial firms and institutes to ensure that our graduates have the required foundation for employment or further education in this rapidly advancing field. Our overarching goal is to create a program that provides an excellent education while also driving forward research and actively engaging our students in the research process. As the presentations at this conference will demonstrate, the advance of quantum computing is changing how we think about computers and science in general. I'm excited that URI is part of this new frontier and that you have joined us today. I echo the thanks offered by Professor Khan to our industry partners. We can't say it enough, to D-Wave, IBM, Quantum, Zapata Computing, PSSC Labs, and Microwave. These types of collaborations are important to building out our understanding of quantum computing and also ensuring our students are prepared for entering the industry. I'd also like to recognize Christopher Savoy, founder and CEO of Zapata Computing. Christopher is a URI alum and a member of the College of Arts and Sciences Advisory Board. He models one of the essential strengths of our university, which is our alumni. They consistently give back, and Christopher's collaboration with the physics department was essential to the development of this new program. And he's also generous with his time mentoring students. My sincere thanks, Christopher. And my sincere thanks to Professor Khan, Professor Srinivasa, and Professor Khanna for their work in creating this program and coming together as the steering committee. In closing, the tagline for the College of Arts and Sciences is putting knowledge into practice. This conference is an important part of that work, along with our new quantum information science program. This conference is the first of what we hope will be many events around quantum computing here at URI, and I hope we will see you back for those events in the future. I'm pleased to pass the mic to my colleague, Professor Benita Srinivasa, who joined our physics department 2 years ago. We are fortunate that she chose to come here, and we're very happy about that.
Thank you very much, Dean Riley. We are blessed to have your dedicated support and enthusiasm, as well as the support of the College of Arts and Sciences and the university in this new endeavor, which includes the launch of the new Master of Science degree in quantum computing and quantum information science program in the Department of Physics at URI. My name is Vanita Srinivasa, and as the Quantum Information Science Program Director here at URI, it is my great pleasure to welcome all of you to this inaugural quantum computing event, whether you are here with us in person or virtually. So first of all, we would like to thank all of our distinguished invited speakers and panelists for lending their time and expertise for this inaugural conference in gracious support of our new degree and program. So thanks to all of you, we are delighted to have a truly incredible program that encompasses everything from the National Quantum Initiative to quantum education to amazing science that ranges from approaches for building quantum computers in various physical systems to running calculations on them. And I am looking forward to enlightening discussions over the next few days, both impromptu and at the roundtable discussion tomorrow evening on the future of quantum computing. The set of topics that will be presented at this conference are taken together serve to very nicely highlight our vision for establishing URI's program as an ideally balanced integration of education and research in quantum information science. That vision has begun with the MS Quantum Computing degree, together with my own research on the theory of quantum information processing with semiconductor qubits and hybrid systems, a topic which you'll hear more about during this conference. I would also like to mention that I have a postdoc position in my group coming up. So if you're interested in getting involved in this research, come talk to me. I'd like to thank my fellow members of the organizing committee, including Christopher Savoy and Gaurav Khanna, who have worked to help put together this amazing lineup of speakers and events and have been instrumental in bringing attention to this conference. Our conference organizing team also includes Amy Harrington in our department, who along with Joanne Esposito and her team have meticulously coordinated the details of the in-person and online events, the agenda, the arrangements for our invited speakers and panelists, registration, meals, parking, and many other aspects, both in person and online, as well as Anuradha Virakodi, who is responsible for the fantastic conference website and all of the content and design updates over the last several months, and has also worked continuously along with our department's lead IT manager, Steve Pellegrino, Katie Babula, James Young, and Matt Santagada and their teams to make sure that we have a smoothly running setup for the complicated coordination of each and every distinct event of this first time hybrid conference. There are many others to thank, and while I cannot mention everyone by name, we are truly grateful to all of you, including our sponsors as well. Finally, I would like to specially recognize our physics department chair, Leonard Kahn, who along with Christopher was responsible for the original concept and development of the MS degree program in quantum computing, and who has worked tirelessly from the beginning stages of planning this conference on everything from the science and coordinating the Cruikshank lecture this evening to the organization, promotion, sponsorship, and logistical details, including taking care of every loose end that no one else picked up and keeping all of us organized, coordinated, and sane. So first, now I'd like to talk about a few logistical notes. We would appreciate if each speaker can set up during the previous speaker's question and answer session, unless your talk is preceded by a break. And to make the Zoom work for our remote audience, before presenting, please make sure that you mute your audio and turn off your camera. And in addition to today's lunch in Higgins and Cruikshank lecture in Beaupre, which you heard about, the extended lunchtime each day of the conference is combined with a poster session, during which you can view the contributed posters that will be set up at the back of the room. To provide more informal space for connecting in-person and remote speakers and attendees, we also have a hybrid in-person virtual hallway that we have set up as a Zoom session in the back room behind the posters. So you can use this setup to have a more casual discussion with your colleagues across locations, and hopefully this will connect our remote speakers and attendees better with those who are in person here at URI. So remote colleagues can also use one of the breakout rooms to have a longer discussion with other remote colleagues. So with that, I would like to begin the conference. And it's my great pleasure to invite our opening keynote speaker, Professor Jake Taylor, to the stage. So Professor Taylor served as the Assistant Director for Quantum Information Science at the White House Office of Science and Technology Policy, where he helped conceive, implement, and lead the National Quantum Initiative from 2017 to 2020. He is the co-founder of and a fellow of the Joint Center for Quantum Information and Computer Science, or QuICS, a fellow of the Joint Quantum Institute, and a NIST fellow at the National Institute of Standards and Technology. In addition to publishing pioneering research in quantum information science over 2 decades, he was a TAPP fellow at the Belfer Center for 2020 to 2021, where he examined methods for integrating public purpose into the development of emerging technology. So Taylor is a fellow of the American Physical Society and Optica and recipient of the Department of Commerce Gold and Silver Medals, the IUPAP C15 Young Scientist Award, the Samuel J. Heinemann Service to America Medal, Call to Service, and the Presidential Early Career Award for Science and Engineering, and the Newcomb Cleveland Prize of the AAAS, among others. And I have had the honor and pleasure to call him my postdoc advisor when I was at the Joint Quantum Institute. So Jake.
So I hope you'll. All right, we have slides. Thank you so much for those introductions. Thank you for URI for getting us started here today, and also for leading the charge in the creation of earlier educational opportunities to enable a workforce that really is quantum smart. It's tremendous to see this combined effort and thrilling to be here with everyone today. And before I begin, I think it's just helpful to remember briefly how lucky I feel, and how many of us do, that we're actually in a safe way in person doing some of this conversation. I know for me, it's my first real work trip in a year and a half. And so I hope you don't mind if we shake off the dust a little bit. Those remarks said, I'm going to talk today about some of the opportunities that are driving this large-scale investment in quantum information science, and some of the challenges that we're looking towards for the nation, for science, and for the world as we try and execute one of the grandest visions that we've had a chance to create as a race. This picture here is a picture of an atomic clock. Not that you could really see it, it's the actual clock stuff's right kind of hiding in here. This is a device made by my colleague, Jun Ye, at NIST in Boulder, Colorado. And in it, you have individual atoms ticking away at multiple hundreds of terahertz with a precision which now enables, well, timekeeping to the end of the universe, but in addition, enables observation of things like the general relativistic redshift of a particle as it moves 1 centimeter vertically. This sort of precision metrology is driven by the advances in the technologies behind quantum information science, our understanding of quantum mechanics and its limits, and is in turn transformative for new technologies. What I want to talk about today is actually this concept of quantum information being what you might call a base technology. Technology upon which other technologies are built. And you're going to hear a lot about this. I don't know if everyone in the audience is a quantum expert. I'm assuming not. And so I will remind you that one of the core ideas in quantum mechanics is that of superposition. So I've labeled here helpfully an arrow pointing down for a state you might call 0, and an arrow pointing up for a state you might call 1 of a hypothetical spin half particle. This sequence in time, going laterally left to right, represents a series of operations that you might apply to that object. The series of operations are called a Ramsey sequence. They correspond to first polarizing this into a known initial configuration. You're at 0 entropy, you know exactly what's going on. Then you rotate this spin into a superposition of both 0 and 1, which is denoted here by being sort of along the equator of this sphere, representing the range allowed down and up. You then let it sit for some period of time called free precession, in which it's allowed to swing about the equator. You rotate it back up towards the top or bottom of the equator, and depending on how much it swings, you'll get different outcomes of how far up it goes. So you're able to catch the spinning around of the object by measuring it to be up or down at the end. You get a probabilistic answer. It's a little bit more up than down on average, for example. And you can interpret that answer as a knowledge of how many times it's spun about in the middle. That's the basis of an atomic clock. And if you kind of watch it go, it's kind of be fun to do in practice, but what you actually do is you actually build these sort of apparatus, this complex device that does it. This is one of the first atomic clocks built at the National Bureau of Standards, what is now NIST today, using transitions in the ammonia molecule. And this formed the basis for a type of timekeeping that no longer relied upon terrestrial references. It was based around the idea that molecules are the same no matter where you find them, or atoms are the same no matter where you find them. And so by relying on the laws of the universe rather than on a human-centric concept like a second or an hour, you can start to create a clock that works anywhere you go. What's a little bit harder to predict, though, is that this advance in timekeeping translates, by our knowledge of physics, that time equals distance under the speed of light to translations of distance, which allows you to, for example, with a constellation of satellites, find your distance to this a set of known objects. And if you know the distance to at least 4 of these objects, you can locate yourself at the intersection of these 4 spheres. And that location process we do with the global positioning system. But there's another thing that's happening at the same time of the atomic clock, and that's the advent of high-power microwave electronics and the ability to start transmitting information in the microwave domain. Just over 10 years later, Penzias and Wilson are testing out their microwave detector outside of Bell Labs down in New Jersey, and they see a spurious signal in their early cellular technology system. That was the beginning of cell phones, 1961. That spurious signal turns out to be the residual image of the Big Bang. It's called the cosmic microwave background radiation. But the technological advances going on behind the scenes enabled these clocks to transmit from space down to Earth to the point that the phone in my pocket and the watch on my hand can receive the signal. And it also opens up the opportunity for the two-way transmission, which of course is what we now know as cellular technology, which combined with knowing where you are produces this very interesting emergent phenomenon, which is pervasive navigation. The fact that I had to ask no one how to get here today, I just put an address into my phone, and through these geographic information systems, through the global positioning system, through an internet distributed across the world, through complex cellular systems, I'm able to get here. That is a few base technologies leading to a very complex outcome. And it's extremely hard to predict the consequences. You know, like I'll come to this in a second, but you wouldn't have predicted from the atomic clock and the advent of microwave amplifiers that work in space that you would disrupt the taxi market in the late 2000s, that we would transform shipping. And so there's an old Danish saying, right? The prediction is very hard, particularly about the future. But you can say this: if you own the base technology, you own the future, whatever it may be. That same clock has been obviously upgraded many times. This was from 10 years ago, making very high quality atomic clocks that are chip scale from my colleagues out in Boulder. There's this sort of path moving from, I apologize going backward, moving from this apparatus, right, which is laboratory sized, forward quite a bit, to this sort of chip scale device. And it's actually part of how you turn these base technologies into technology. It's not just you realize it in the laboratory, but you work through the hard process of making it into a repeatable, reliable, engineered system that you can then use to do some other interesting thing, including other experiments. I'm a scientist at core, so I'm excited about that. So let's talk now a little bit more broadly. What does quantum information science bring to the table? Why are we doing this at a sort of intellectual level? And I like to think about the 3 main contributions that quantum information has. The first is in understanding the limits of measurement, of how you see things, of where you can detect something to be, and other units like mass and temperature. We call this field quantum sensing, and it basically breaks down to 2 different areas. One is what I've talked about a little bit, the idea of deriving accuracy from physical law, rather than from some sort of artifactual standard. This culminated recently in the adoption of what's called System International, but we call it today the Quantum SI, because every one of the standards that we use to underpin our commerce now relies on quantum mechanics. The last one was the kilogram sitting in Paris. We finally got rid of it. Took 20 years of international diplomacy and 20 years of scientific development. We got it done. But the key idea is very simple, which is you take an underlying physics concept, like atoms are indistinguishable, and you use that to create a time standard. Or that the speed of light is constant, and use that to create a distance standard. Or even that electrons are quantized, and they all have the same charge, and use that to make a current standard. But the other approach that's very interesting is what we call new modalities of measurement. That is measuring in an area that you just didn't have an apparatus that worked before. So we've seen this now in magnetic resonance imaging, or MRI, which I know some of you in the room have had an MRI, where you would love to be able to not have to sit inside that big tube. That big tube is a very high magnetic field magnet, and it has to be super cooled with liquid helium, and it's kind of a pain to work with. But if you have much more sensitive magnetic sensors, you could get rid of the big tube and instead have the whole room be magnetized. And so there's been very recent developments up at Mass General Hospital and a few other places demonstrating that you can in fact do this sort of free field MRI using quantum sensors, in this case, atomic sensors. Another challenge has to do with that when you try and estimate how far away something is, you can send light at it and it bounces back. If everyone has been caught by one of our distinguished law enforcement professionals who are measuring how fast you're going, right? You know that there's a way to figure out the distance with light. But the challenge is that light is actually quantized. So if you want to infer the information, you need to get enough of the light back. And if to do that, you need more and more laser power to get more and more photons to infer ever narrower distances. And at some point you run into limits because all those photons hitting the system actually make it move. It's called back action. This is one of the fundamental things of quantum mechanics. And so, for example, at the Laser Interferometer for Gravitational Observation, or LIGO, you actually have a scenario where the first results where they saw inspiraling black holes, they could see high luminosity events, but they couldn't see things that were a little bit smaller in mass. But as they upgraded their sensors and started using what's called squeezing, which is a type of entanglement used in quantum sensors, they're able to go beyond those limits. And the third thing is just some things that are just really hard to see, like brain activity, or for example, cellular inside a single cell looking at particular cellular functions. We can start to do that now with quantum sensors, simply because they operate in a regime that no other sensor operates. Another area that is of deep interest and the main focus of today's conference is quantum computing. And in quantum computing also kind of breaks into two main categories. On the left, you have what is generically called a quantum simulation, and it's essentially solving problems that depend on quantum mechanics. Chemistry, material science are the big ones. There's some things in biology as well. If you want to understand at a simplistic level what's going on, I will give you an analogy. As you may be aware, the fluid dynamics is a really hard field. That was something we knew before we knew about quantum mechanics. And in particular, solving the equations of fluid dynamics represents a computationally hard task. It's NP hard in general. So that means that basically any computer will eventually fail trying to solve this problem. So what do we do in practice when we want to design an aircraft? Well, we use complex numerical simulation on classical supercomputers, and we complement it with simulation on a system that's very tightly controlled that is realizing Navier-Stokes equations, in this case, a wind tunnel. In the same way, you can use a very tightly controlled, well-understood quantum system, like today's small-scale quantum computer or another complex quantum device, in order to emulate a particular scenario that you'd like to understand better. And then complement it with both mental and theorist-type understanding, but also large-scale classical supercomputing applied to understand those problems. And that's advancing our knowledge of how we do quantum mechanics, what it means, makes better chemistry, and makes better materials. I'll talk towards the end about some of those options, but I think we'll have some talks later on digging deeper on that. But the long-term future is really the programmable quantum computer, which is a large-scale device that executes arbitrary quantum circuits. And that's the target, that's the 10-year goal. And that device enables areas from understanding some things in financial markets to optimization, to things like code breaking and other more esoteric algorithms, which we know how to write down, but we don't know their application. So it's a very interesting field. But actually there's a third area, and that is quantum networking. So you build these quantum computers, so what? The individual computer on your desk is made infinitely more powerful to you because it is internetworked. The individual devices that we build, these sort of quantum gadgets, are very hard to make larger past a certain point. And so at some point, we're going to need to derive more power and utility from them by networking them, by connecting them together. And this is the field of quantum networking, which is really the most nascent of the three. It has some immediate applications, primarily in what's called quantum key distribution or quantum communication, in which you use the inability to measure without disturbance in order to ensure the creation of shared randomness, which is a core element for cryptography protocols. But more interesting are things like inter-network sensors. I told you about how quantum sensors get into these new modalities or push at new limits. And by networking them together, you have distributed systems that can achieve those goals. That can be very large, particularly in astronomy and also terrestrial detection. It's also worth mentioning that one of the interesting areas here is going to be the intersection of these quantum technologies in space. We can talk about that offline if you're interested. But kind of the long-term future is what we call quantum cloud computing, quantum computers connected with a quantum cloud. And that opportunity space is something we don't really understand yet. We know there are algorithms like fully homomorphic encryption in which your data center executes code that it doesn't know what it was on data that it doesn't know what it is and returns results to you. That's something you cannot provably do classically. But we don't know beyond that. And so it's going to be very interesting in the 20-year horizon when we look at internet-worked quantum devices to understand how that changes our society. Okay, so that's some good foundational concepts, I hope. And I now want to talk briefly about the National Quantum Initiative, or also known as A Physicist Goes to Washington. So I, of course, am a scientist by trade, and I didn't start my career trying to get into policy. I've been working at NIST since 2009, where I joined as a staff scientist and slowly worked my way up. I, of course, affiliated myself to the University of Maryland through the Joint Quantum Institute, and then later through the Joint Center for Quantum Information and Computer Science. Actually, we put that joint center together because at the time, it was impossible to hire a quantum information theorist working in quantum computing in a physics department. And so NIST worked with the University of Maryland's computer science department to essentially leverage themselves into the physics department and get computer scientists doing this stuff with the physicists. And that was a good example of a high leverage moment. Not a lot of government effort, but enough. And so in 2017, towards the tail end, I had organized a industry day for quantum industry because my boss at the time, Carl Williams, and I had canvassed the space, and we realized that there's a lot of these companies starting up, like Zapata Computing, who had grand visions and without support would all fall on their faces. And so we canvassed industry. We discovered that industry totally didn't want help, except they really did need help. It was the usual, actually, problem the government confronts. And so when I was asked to go down to work at the White House Office of Science and Technology Policy to implement a solution to this problem, any solution would be fine as long as it was successful, I was honestly thrilled. And so I went downtown and started in December of 2017. And one of the first things that we did is we started working with the community who was going to be affected, primarily the research and development community in this nascent industry, along with the elements of society that are going to be affected by that. You can't just create an industry, you have to create a culture around that industry that's beneficial for the US. So that first effort culminated in a summit we ran at the White House, which is what this slide is from. There's France Cordova from the NSF speaking along with her colleagues from the DOE, NIST, and Department of Defense, where we gather this community together and say, here's what we think the policy could look like. Give us the feedback. And that result was this National Strategic Overview for Quantum Information Science, which is the US strategy, you're bored or you just want to hear the short version of it, it's on quantum.gov. We kept it short. The whole thing is 20 pages. That's the US policy, and that's our strategy. It's very simple. First, recognize that the government's role here is making certain we're getting the science right. There is a tremendous amount of challenge ahead of us. And the idea that government's in a technology development program didn't make sense at that time, because we have an innovation and entrepreneurial system that is working on the question of how do you market quantum computing. That's not a government task. But what is a government task is making certain that the US has the best technological and scientific capability to execute. We need to build a very large and diverse workforce. We call it quantum smart. This means that it doesn't necessarily require a PhD level knowledge in 3 different fields, which is what it looked like if you were in 2017. But nonetheless, that you are aware of how quantum can impact your particular industry or your particular area of interest, and that you can take that with you wherever you go. Develop the right industry engagement, the key infrastructure and support. Do this while driving economic growth and balancing that with some national security considerations. I mentioned that quantum computing has the capability to break our modern cryptographic systems. And we're in the process at NIST of rolling out what's called post-quantum cryptography or quantum-resistant cryptography systems to replace that SSL little lockbox on your browser with something that's resistant to quantum computing attacks. That process is ongoing. It'll be roughly completed by 2030. Right? And so one of the key things here is that as we go, we don't want to just upend the entire apparatus if we don't have to. And then finally, to continue to develop the international cooperation and collaboration, the US working with like-minded partners is our path forward. The supply chain is global, the workforce is global. To close our minds and thoughts to the opportunities around the world will essentially put us behind in the race. After this policy document came out, the Congress put together, has been building a bill. That bill then built with this policy to create the National Quantum Initiative, which was signed about a year after I started. And it basically sets up this 11-year sustained effort. So we have till 2030 to get the science right. By then, we darn well better have everything else going. But it's centered around the civilian side with the Department of Energy and the NSF, both creating large internal programs and new centers, and NIST leading in the industrial efforts, along with its expansion of its core standards programs around quantum. The coordination using both the National Science and Technology subcommittees, along with the National Coordination Office and an external advisory committee. That's the core of the idea. How do we do it? So first, we need this innovation ecosystem really working for us. So I worked closely at the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science, between the government and academia, and then later government, academia, and industry. We made a bunch of mistakes. I also canvassed the literature to understand what other things, but the basic thing is, thank you, chat. The basic thing is that you have lots of different ways you have to go, but fundamentally you need a long-term focus, co-location, dedicated infrastructure, and a fluidity in how talent flows. This stuff is funded on the order of $1 billion a year over $1 billion over 5 years in terms of the centers programs. And you can read about it at the Department of Energy website and the National Science Foundation website. I also need to coordinate industry. So this is a pre-competitive space. The market for quantum computing today is pretty small. But Amazon Web Services is one of the few that allows you to buy quantum circuits, and it's 0.035 cents per circuit. It's a little bit early. So when it's an early space, we have these authorities to create consortia, which essentially recognize that companies can work together in pre-competitive areas without falling afoul of antitrust law. And that's been a very powerful driver of development in other fields. There's about 350 consortia that have been put together since that act was signed back in the late 1970s. The idea, though, is to share the R&D, tech development, and exploration costs across multiple partners. And this culminated in the creation of the Quantum Economic Development Consortium, which you can read about at quantumconsortium.org, which is a private industry-led but US government-supported consortium in the space, and is organized by SRI International. And then finally, on the workforce. So, biology, with the expansion of the NIH 25 years ago, started running into this challenge of the biology pipeline. How did they solve it? They did a lot of work on that. I found this slide very helpful to see, like, this is how the NIH was thinking about it, right? They have the 16,000 students coming in, some of them drop out, some of them leave the US, some of them go elsewhere, then they come back in the non-research jobs or in other related science jobs. There's this infinite loop of postdocs, which is something we want to avoid. There's this people going into tenure, people going into industry. This is very different than what quantum was in 2018. But this is what quantum is tending towards, which is this sort of interesting, some people going into faculty, many people going into industry, many non-research but science-related jobs becoming available. And so the point, though, is that if you start here, see where they start biology PhD programs, all of our research, which we've had 25 years to learn since the NIH started their programs, tells us that that's way too late. Because all that does is it takes people who are already at the very top and helps them get forward. It doesn't broaden the workforce at all. It doesn't get a diverse set of voices or ideas into the space. And it doesn't do what we did in the 1960s with the Apollo program. Like, the median age of an engineer in the Apollo program in 1969 was age 23. You don't get here at age 23. But nonetheless, that's actually where quantum industry has its greatest opportunity. And so we started in order to solve this, we first need to break down these disciplinary barriers between computer scientists, physicists, engineers, mathematicians, and others. But we started the National Q-12 Education Partnership, actually to get the focus on the early education part, 7th grade and onward. And you're going to hear about that later this morning. And that goes up into the community colleges, up into the technical colleges, up into the undergraduate only institutions, up through the HBCUs and minority serving institutions, up to the R1 institutions. Like, it's meant to be not a pipeline, but a series of connected webs of opportunity. And at every step of the way, there are actually off-ramps for people who are interested but don't want to continue pursuing education. And that's kind of the really should be the goal. This is not like, I need the perfect person. It's actually, I need to recognize that people bring different skills to the table, different viewpoints to the table, and that is a benefit to my operation. And we also want, of course, the international part to work. One of the last things I did in my official duties before switching to COVID 900%, which we can talk about some other time, was going to Tokyo to help sign the Tokyo Statement on Quantum Cooperation, which is the first of its kind, indicating that we're working with like-minded partners. More to come soon. And then we put together the Quantum Coordination Office, and you can read about that at quantum.gov. I have to say I have a little bit more I'd like to cover, but I think we're really close to the end of our time. I think I'm supposed to stop in nowish. And so instead of telling you about how we can measure dark matter, how we need to use machine learning, I'm going to skip right to the end. And talk about the field of dreams. Why are we doing this? It's because we believe that there are transformative opportunities ahead of us. This picture is a famous park up in Boston. Some of you have been to. And as you may be aware, when you play baseball, there's small ball, where you try and advance runners one base at a time. And then there is really going for the fences, the home runs. And one of the interesting things is that in quantum computing in particular, we actually know that these home runs exist. We figured out how big the green monster is. We know how hard it is to hit it, but it's there. And that basically means that there's known killer apps. It's quite different than many other fields of speculative technology, in which you hope that there's a killer app, but you can't prove it. We actually have mathematical proof these killer apps exist. But the problem is that we're right now doing small ball. We're trying to sort of hit bunts into the infield in order to advance a runner that's not yet on base. So we have to figure out the path to bridge from here to here. One thing is what are called noisy intermediate scale quantum systems, which have related algorithms that work. But more generally, there's a lot of options in understanding new paradigms for machine learning, for using quantum sensors with quantum computers. But it's this outfield where the real work's going to happen. And that's where you've got new algorithms, heuristic algorithms, new simulation approaches that are integrated, compilers and programming systems that we need to build. And fundamentally, the way I see it is what we really need is people working hard taking a systems engineering approach to creating quantum machines that matter. If we can achieve that, we will see a transformation. And with that, thank you for your time. I'll take questions.
Thank you so much, Jake. That was a fantastic opening keynote talk. So questions from the audience
Also from Zoom.
and from Zoom. So I have a question. So what would you say is sort of the best way for a place like University of Rhode Island to get into the conversation at the federal level on building a quantum information science program from the bottom up?
Yeah, so thanks for that question. So the better person to answer this, by the way, is going to be Charlie tomorrow, because he has the most recent information. However,
All right.
that's my successor at the National Quantum Coordination Office. I'm going to come back over to the microphone. So the question is, how does an institution like URI, which has a research arm, which does a lot of education, how does it get in? And the answer is got to be, first of all, there's a federal component, right, in which you work with the National Science Foundation, which has yet another set of new programs, right? We're continuing to expand the availability of these government programs. The expansion is governed, really limited by the workforce availability and pipeline growth. And so obviously, applying both independently for a smaller scale, but also in conjunction with other institutions is a very powerful pathway forward. The Department of Energy has a bunch of big programs which involve, among other things, connecting to the Department of Energy laboratory subsystems. So in this case, Brookhaven being the closest one. And that's a set of opportunities where when there is joint benefit to be had, there's a real opportunity. And then the third is working with industry partners in either just pairwise, and I think you're already doing that to some extent, but also with the government as well, in which you become a test bed or a testing zone for new ways of trying out quantum education and for new ways of trying out research both on the application side and on the fundamental side. So the bad news is that all of these require a lot of work, because I come back to this people working hard part. Yeah, there's no substitute. One of the things when I was working with Ash Carter last year was this continuous refrain, which is that any technology that's worth building has required thousands of people dedicating their lives to it. And that is not just about the technology itself, it's also about the organization around it and the groupings that make it happen. But the last point is, wherever possible, play to your strengths, right? So Rhode Island has a vibrant economy. It has key needs in key areas around particularly clean growth and oceans. And if you look at the intersection, for example, of these material science developments that are made possible by quantum computing systems, and what you need to make clean energy work, and what you need to understand certain aspects of the chemistry and marine environments, right? There's some opportunities. So it's also leaning into your strengths where you can. I hope that's helpful. I see we have a few questions in the Q&A. We can also.
Yeah. So we have a question that's, how might small startups interface with the DOE and other grant programs in this space?
Yeah. Thank you, Michael, for that question. So the DOE is its own very unique entity. And I will say that the best way to engage with the DOE is not to go to the leaders, to the headquarters down in Washington, DC, but to go to one of their 16 national laboratories and literally talk to researchers there and see and find your connection. Find the one where there's a intellectual or technological or scientific connection. And then with them, you work with them through their DOE program managers and the likes in order to generate sort of nascent growth. That's for startups. That's for small groups of people. If you're a large established company, I don't need to help you. You probably got to figure it out better than I do. But that's my general approach there. Then the NSF has a somewhat different approach. The NSF has these technology accelerator programs, and I highly encourage you to read about them. The NSF is very public about all its programs and how they operate and why you should do them. And the technology ones are very good for non-dilutive capital. So definitely go for it. And finally, the Small Business Administration does loans. And they're quite good, right? They're the biggest driver, the biggest investor in US small business is not venture capital, it's the Small Business Administration. So don't hesitate to use them.
Thank you. So we have,
Question in the audience?
yep, question.
Thanks for the nice talk, Jake. I was wondering if you could comment a bit more on the opportunities in the space of quantum networking. But one of the interesting physics outcomes over the past few years has been gravitational wave detection and LIGO. And one of the things that's helped with that program is just having different detectors that could correlate signals. But you could imagine amplifying this in space with larger scale quantum networks and making large baseline detectors and arrays, things of that nature.
Yeah, thank you for that. So I did mention briefly how the sort of quantum Internet of Things takes what you can do in the sensor space when it's distributed and provides just a little bit better performance. So in practice, when you ask what is the role of entangled sensors at distance, it rarely does an improvement in your precision per se. One of the things that it can improve is your resolution, your ability to resolve distant objects. So in astrophysics, that's pretty important because you like to, for example, see a planet separated from its star. Another opportunity is actually in things like clock synchronization. So the global positioning system is not limited by the individual clock's performance, but how they synchronize with each other. And if your synchronization link is limited by shot noise, which some of them are, so that is to say that your lasers can be no more powerful because you're up there in space, you can move to entanglement through a quantum internet system in order to get further performance out of it. So for example, the GRACE mission, GRACE 3, which is a mapping mission of the Earth's gravitational, two satellites flying in formation around the Earth, mapping the Earth's gravitational field. Right, that's limited in part because of power limits of what you can put in space. And so if they could add squeezing, so that's the type of quantum entanglement for distributed that you can build through a quantum network link, they could do better. So those are sort of the opportunities. Yeah, I think we have time for one more, two more.
Thank you, Jake. I'm interested in knowing the relationship with the US Congress. We know some people are really interested in this, but specifically OSTP and the US Congress now versus a few years ago.
What is my opinion about the US Congress?
No.
Oh, okay. That sounds dangerous.
No, it's the relationship in terms of, awareness about quantum computing and QuICS, like also within the last 5 years, like the previous Congress and now.
Oh,
overall.
so this is an interesting question, which has to do with, how has the changing political winds changed the perception of programs like the NQI and of the importance of quantum? What's very interesting, NQI was always a bipartisan bill. It passed overwhelmingly from both parties. It was written by a bipartisan committee. The staffers who worked on it were bipartisan. And we saw zero change in interest in change of administrations. It was a high priority for the previous administration. It's a high priority for this administration. I think we understand that. Said at the beginning, if you don't own the base technology, you're losing. If you own the base technology, you own that future. And our politicians understand that. They have other needs too. I completely respect that, but they understand that. And so I think that the biggest shift I've seen recently has been a push to move from the science first approach I've mentioned to get closer to the technological acceleration. And we'll see with some of the bills going through Congress, the timescale that's going to be. But I encourage you to ask that question again when my successor, Charlie, is here tomorrow. He was working directly on that problem. We might be out of time.
I think we're out of time. So thank you very much, Jake. Appreciate it. So our next speaker is Rick Mueller from Sandia National Laboratories, USA, who will be joining us remotely. He's the senior manager of the Quantum and Advanced Microsystems Group at Sandia. And he manages the Sandia portfolio in quantum information science. So he's also the Deputy Director of the Quantum Systems Accelerator, which is one of the 5 DOE National Quantum Information Science Research Centers, which is co-led by Lawrence Berkeley National Laboratory and Sandia, and uses and includes collaborators at Harvard, MIT, Caltech, Duke, Berkeley, and other institutions. So Rick came to Sandia in 2003 after serving as the director of the Materials and Science Simulation Center at Caltech, which followed postdoctoral fellowships with a Nobelist Aryeh Warshel at the University of Southern California, and doctoral work with Bill Goddard at Caltech, all in computational chemistry. And he did his undergraduate work in chemistry at Rice University and the University of Oxford. So prior to joining MESA, Rick was a distinguished member of the technical staff in the Center for Computing Research at Sandia, working in electronic structure theory and quantum device modeling, and a manager in the Material, Physical, and Chemical Science Center. So Rick spent 2016 to 2017 in Washington, DC as well, working for the National Strategic Computing Initiative. So welcome, Rick.
Thanks very much. Can someone give some sign that they can hear me at this point? Okay, thank you very much. Okay, thank you to Vanita and the University of Rhode Island for my invitation to this conference. And I'm very sorry that I couldn't be here in person. Sandia is still reluctant to start general travel at this point, so I am stuck in Albuquerque here. And as well, thank you for Jake Taylor for that great introduction, both to the field of quantum computing and to some of the political movements that Jake and others did to enable us to do quantum research at a larger scale. So what I want to do is talk a little bit about how we're going to bridge Jake's metaphor going from small ball to swinging for the fences a little bit. Before I start, I wanted to talk a little bit about just what Sandia does in this area. Sandia has a program in quantum information science. It's about 15 years old now. We have, it's a broad program in that we have research going on in all of the 3 areas, the sensing, computing, and communications and networking that Jake mentioned. And it's fairly mature in that we've got a couple of platforms, namely a trapped ion program here, which is the device of which is shown in the lower left, that we distribute to the wider world as well. So Sandia has working devices in multiple technologies, and along with the experimental capabilities, we have a broad theory effort that has expertise in characterizing quantum devices, in benchmarking them, and in estimating the resources that are required for high impact applications of quantum information science. Just a quick advertisement, you can email quantumjobs@sandia.gov, and we're always looking for graduate students, postdocs, and mid-career scientists here. Oh, I'm sorry. Okay, so I want to begin the talk by talking about test beds and how we can understand a little bit better what resources are available to devote to quantum computation. And so, you know, building quantum systems that you can probe and investigate is expensive and it's complicated. It's very exciting now to see a number of commercial systems that are on the cloud through Amazon Web Services or through other commitments. But those services are often difficult to get close to the hardware on. And so a program started 3 years ago by the Department of Energy's Advanced Scientific Computing Research Office, which is part of the Office of Science, to fund open test beds to address both of these problems. These test beds were to be free to use and access, and provide lower level controls over the devices, to make open characterization and benchmarking of these devices, and to even be able to get down to things like how you can shape the pulses that control the quantum operations, as well as how you can change the compilation of the quantum circuits on these devices. So in the initial instance of this program, the Department of Energy started 2 different testbed programs. One at Sandia National Laboratories called the Quantum Scientific Computing Open User Testbed that uses trapped ions. And trapped ions have a number of very attractive characteristics for a device like this, at least for small collections of trapped ions. You can make all-to-all connections between them. And in the lower left, I'm sorry, we see the QScout logo, which kind of makes reference to the fact that you can connect any ion in the QScout apparatus to any other ion. These are generally parallelizable calculations. They have long coherence times and low crosstalk. Superconducting technologies, which is what our colleagues at Lawrence Berkeley National Laboratory use, have a complementary set of capabilities. In general, the gates that superconducting devices use are faster. Superconducting devices themselves look a lot like control circuits, and superconducting processors have excellent classical control. They have configurable qubit connections, and the devices at the Advanced Quantum Testbed can be configured either as a 3-dimensional vector space or a 3-dimensional qubit spaces, QTrits, or 2-dimensional qubits, as traditionally is used. So I'll talk a little bit first about the platform at Sandia that we call QScout. So QScout is based on trapped ion technology. Sandia has manufactured surface traps for trapped ion quantum computing for around 10 years now, partially funded by the IARPA MQCO and logic programs. And we distribute these traps to the world. But until the DOE testbed program started, we did not have ways to actually use these devices to make a user facility that we could allow other people to use as well. So you can trap multiple ions in the linear traps that we have developed at Sandia here. And for various reasons, the QScout processor is based on trapped ytterbium ions. And we are on the journey from very small devices that only have 3 qubits, building up to what we think will be a maximum of 32 qubits with this device. QScout uses Raman lasers to perform the single and 2 qubit gates that it uses. QScout has developed its own programming language called Jackal. Jackal stands for Just Another Quantum Assembly Language. And the goal of Jackal, and the reason that we wanted a specific language, is that on a lot of existing platforms, you have limited control over which processor a part of a quantum circuit would run on, and whether there were additional simplifications made to the devices. So for example, In a lot of the commercial platforms, if you run two consecutive X gates next to each other, the compiler will be smart enough to know that that is equivalent to an identity gate, and we'll just remove that from the calculation. But for benchmarking and analyzing these devices and really studying what they're doing, we want the freedom to really say, no, we want to actually run 20 X gates consecutively. Maybe we wouldn't do that precise circuit. And so the Jackal language gives you low-level control to which processor various circuit elements are run on, and timings and delays and things like that. And then QScout as well has a team of Sandia scientists that are available to work with the user proposal teams to run the projects and help them understand the results of those runs. So the current devices, we are now currently moving from generation 1 to generation 2 of our QScout platform. We're moving from 3 to 10 qubits at this point. These are fully connected. We're seeing maybe 0.5% error for the 1 qubit gates and maybe a 2% error right now for the 2 qubit gates. These are individually addressable. They have low crosstalk and low preparation and detection error. And as I said before, we're moving towards more powerful processors here. We think that our control devices will max out at around 32 ions. And we're developing things like partial measurements and higher fidelity gates to enable more sophisticated circuits with them. Another unique capability that QScout offers is under the hood access to what quantum operations are being performed on these devices. So we've developed a low-level control language called octet that speaks to the system-on-chip processors that actually control the pulse shaping for the devices. And that access is also available through the Jackal control language. So not only can you change the circuit, but you can in fact change the gates that that build up the quantum circuit as well. And the goal is to provide external users as much access to the fundamental quantum devices as we can offer. So we just finished round 1 of our user proposals. We started running user code in spring of this year, even before we had put the finishing touches on the 2 qubit gates that we use. And the first set of user proposals focused on a combination of benchmarking proposals, some low-level simulation proposals, and gate optimization. And it was, just speaking as the manager, not a researcher on this effort, it was extremely beneficial to have a bunch of teams that were external to us and helped us develop the system in ways that we hadn't anticipated we'd need. So in this first period, we had proposals from the University of New Mexico, from Oak Ridge National Laboratories, from Indiana University at Bloomington, and from the University of California at Berkeley. And these exercised various aspects of the QScout architecture. We have not yet started the second round of user proposals on this, but we have selected 6 proposals for the second round here from the Johns Hopkins Applied Physics Laboratory, from Supertech, from the London Center for Nanotechnology, which will be our first international proposal, from Lawrence Livermore National Laboratory, from IBM, and from Indiana University. And we're looking forward to offering more sophisticated capabilities here. This will be the first version of the QScout testbed that will offer pulse level control, which should give additional sophistication to these devices. And we're looking forward to then seeing how the user proposals drives the QScout platform development in directions that we didn't anticipate at first. So if you're interested in interacting with QScout, like I said, our second call for proposals is closed, but we're anticipating having the next one roughly in spring of 2022. We have a website here, qscout.sandia.gov, as well as an email address, qscout@sandia.gov, both of which you can use to be notified of upcoming opportunities. We try to make it as easy as possible to interact with the QScout capabilities. We only require a 2-page proposal at this point. And we have a team that meets to assess these, that has people internal and external to Sandia. And once we've accepted proposals, we have tutorial days and meetings between the user teams and the Sandia teams to discuss implementation and to help with the data analysis. So our colleagues at Lawrence Berkeley National Laboratories has a complementary testbed, as I mentioned, that uses superconducting technology. Irfan Siddiqui is the director of the Advanced Quantum Testbed there. And the AQT has similar goals to QScout. It is to provide access to quantum resources to support those user proposals with a team that is trained and expert in working with them. One really cool thing that the AQT offers is multiple quantum processors, multiple different qubit architectures that you can use to explore how different processors, different qubits affect the overall fidelity of those devices. Whereas in QScout, we have to break vacuum and warm up a device every time we swap in a new processor. The superconducting devices can put multiple processors into the fridge, and you have access to those as part of QScout. And the AQT offers similar deep exploration and close to the hardware investigation of these devices. So I've covered most of these. The AQT provides an open programming interface. They provide access to cutting edge control devices. Specifically, they use Zurich Instruments control devices, and they have an in-house custom modular solution called QuICS that they use that's built upon similar technology as the Sandia octet technology is. They've purchased a large Blue Forest dilution refrigerator that has 160 RF lines. The fridge operates at 10 millikelvin. And they have a partnership with Bleximo that has set up the fridge in a way that is optimal for quantum processor investigation. And the current chip that they're using is an 8-qubit transmon ring. They have high coherence times in these devices, and they're exploring developing and introducing new processors to that as well. The AQT had 7 user proposals in the first round, and the second round for proposals is currently open, and the email address, well, so if you look up AQT at Berkeley Labs, you can get in contact with the team to submit a user proposal. So some select proposals in the first round, Lawrence Livermore National Laboratories looked at simulating quantum, in simulating nuclear physics. Supertech looked at control devices. And Sandia ran some of its scalable benchmarking capabilities on the AQT processors. So again, the website here is aqt.lbl.gov/new users if you're interested in submitting a user proposal for this. So in the previous talk, Jake gave a great introduction to the National Quantum Initiative. This is something that Jake was instrumental and foundational in supporting and developing. And Jake mentioned the development of the national strategy here that provided the roadmap for what aspects of quantum information were critical to pursue for the US government. When the National Quantum Initiative Act was signed in 2018, it outlined opportunities for the National Science Foundation, for NIST, and for DOE. And so I'm going to be talking about the DOE ones because that's where I work. And a little over a year ago, the DOE Office of Science funded 5 different National Quantum Information Science Research Centers. And I'll be talking about the one that Sandia and Lawrence Berkeley National Lab co-lead, called the Quantum Systems Accelerator. But there are other similar research centers that have been developed at Brookhaven National Laboratory, at Argonne Labs, at Fermi Labs, and at Oak Ridge National Laboratories as well. And so, the quantum information, the Quantum Systems Accelerator focuses specifically on quantum computation. And the goal of this effort is to start understanding the technologies and the research directions that we need to go from, again, this generation of computers that we're calling noisy intermediate scale quantum devices, NISC, which you can think of as the kind of technologies that are in the current test beds, let's say, or in some of the commercial offerings as well. And the metaphor here that we probably overuse is that when you're hiking in the mountains, sometimes you don't know the path up to the high peaks until you're standing at the top of some of the foothills here. And what we would like to do in the Quantum Systems Accelerator is stand on the top of NISC technologies. NIST technologies have developed a lot of really compelling capabilities. We've seen our first demonstrations of coherence. We've seen strong theory development that talks about what the possibilities of these devices are. But they are a long way away from universal fault-tolerant quantum computing that we know will be useful and have some really nationally beneficial applications. So what we want to be able to do is understand, explore some of the pathways and understand what the most important pathways are that will lead us over the next, let's say, 10 years to develop more capable quantum devices. And as Vanita said in her introduction, we're absolutely delighted to have really a first-rate team of collaborators working with us in this. And so the goal then is to start benchmarking and estimating the performance of algorithms and applications that we know will be meaningful to understand their limitations. And this is a process that the DOE calls co-design, indicating that one wants to simultaneously vary the applications one is going to do with the hardware and kind of co-evolve those two capabilities together. This is something of an eye chart here, so I'll just speak quickly to it. We have a number of, well, we have very many research paths that we're pursuing here. One of the distinguishing things that characterizes the Quantum Systems Accelerator is that we're looking at a variety of different qubits. So in addition to superconducting devices, we're looking at trapped ion devices and neutral atom devices as well, because we believe that we can understand what algorithms can be specifically tuned to take advantage of different platforms, and that will be important in the near term. So we have this very broad exploration going from the material science to the qubits, to how you make nascent processors, all the way up to how we can create specific applications that will serve as pathfinders to future technology development. We're still in the early stages of the work, but we're delighted to start seeing some near-term high-profile publications come out of the Quantum Systems Accelerator. Just to highlight a few here, a group out of NIST Boulder has used penning traps to create two-dimensional arrays of trapped ions that can serve as high-fidelity quantum sensors for displacements and for electric fields. One of the major avenues that we're looking at through the Quantum Systems Accelerator is how can we go from simple devices that have perhaps limited connectivity to devices that have 2- and 3-dimensional connectivity. And the penning trap work is one of those examples of how we can start building out those capabilities. From the Lucan group at Harvard, we've seen a recent Nature paper that looks at 256 atom programmable quantum simulators for looking at things like spin liquid simulations. Neutral atoms have matured a huge amount in the last 5 years. They're now able to make densely packed 2-dimensional arrays and to arrange those arrays of atoms in different types of lattice architectures. And the paper out of the Lucan group explored some near-term methods for simulating spin liquids in those devices, as well as exploring topological properties of those devices. And out of the group at Lawrence Berkeley National Laboratories, we've also seen novel algorithms be developed to simulate first-order phase transitions and topological phases in ways that are much more robust. And so this is the technique called the rigorous renormalization group, and the paper in PhysRev B explores some comparisons between the stability of these simulation methods comparing to traditional methods like density matrix renormalization group. And so with that, I think I'm just about out of time. So I'd like to thank you for your attention here. We've got some pictures here of Susan Clark, who is the principal investigator of the QScout architecture, some of the Sandia clean room supplies, the team at Lawrence Berkeley National Laboratories, and the collaboration team that forms the Quantum Systems Accelerator. Time permitting, I would be happy to answer any questions. Thank you.
Thank you very much, Rick. So questions from our real in-person and virtual audience. Yes, you can come up to the mic.
Hi, Chris Larakis from IBM. You've talked about a pretty marvelous test bed. I'd be curious to know if you've had any thoughts on providing hardware test beds for engaging universities and other places to start educating the workforce in a hardware sense rather than the software sense.
That's a great question. And that is important to us. So our explorations here do include technologies that allow you to explore the hardware, but at current, we're not doing things like distributing devices with specific instructions on how you can build your own quantum resources, which is how I understood your question. but that is something that we're very interested, and we're kind of developing nascent ideas with some of our closer collaborators. I think that's really critical to develop quantum to the degree that we want to. And as those are important to you, please communicate so we have ways of contacting, let's say, both of the testbed teams in this presentation. But please contact me or contact our colleagues at Sandia or at Lawrence Berkeley National Laboratories, because that is something that we think is important and that we're just starting to explore right now.
All right, thank you very much, Rick. So let's thank Rick again. So that's all the time that we have questions, for questions. So now we'll take a short break, and we'll be back at 9:45 for Senator Reed's remarks. So thank you.
Ethan, audio is off, but I can still see you. Logo is still flipped. Ethan, filter looks good now. Give me a thumbs up if you can hear me. Thank you.
Hello, for those of you who are just joining us, welcome to our Frontiers in Quantum Computing Conference. This conference is a celebration of the launch of our MS degree in quantum computing, which also has a 5-year bachelor master's option. This is in keeping with the Quantum Initiative, National Quantum Initiative, whereby we're trying to train a workforce to prepare for the quantum revolution. It is now my distinct pleasure to introduce Dr. Peter Snyder. Dr. Snyder is Vice President for Research and Economic Development at the University of Rhode Island. He is also Professor of Biomedical Sciences. Remarkably, he's also a scholar in residence at Rhode Island School of Design. Previously, Dr. Snyder served as Senior Vice President and Chief Research Officer for the teaching hospitals at the Warren Alpert Medical School of Brown University. Dr. Snyder is a fellow of the American Psychological Association, and his most recent book focuses on the management of scientific integrity within academic medical centers. It's my privilege. Dr. Snyder.
Thank you very much, Dr. Khan, and welcome everybody. This is a special day for the University of Rhode Island. Really, our special guests, the most important guests here are our own students. And I know most of you have young, strong legs, but there are lots of seats up front, and please don't stand the entire morning. There are seats to be had. But thank you all for attending this morning. This wonderful conference is hosted by our Department of Physics and co-organized with our newly formed Research Computing Office within URI's Information Technology Services. It's a special honor to welcome Senator Rhode to this event. And I would also like to thank our industry sponsors who made this day possible. This conference was organized to mark the launch of URI's new graduate master's program in quantum computing, to be led by one of our conference organizers, Dr. Vinita Srinivasa. I would also like to congratulate the other 3 organizers of this event, and I know that President Parlange in his remarks will name them all, so I won't do so here. However, I do want to take one moment to congratulate one of the conference organizers, Dr. Gaurav Khanna, Professor of Physics and Director of Research Computing at this university. He was just within this past week elected as a Fellow of the American Physical Society, an honor that is reserved for only a few individuals who have made truly important advances to the field. Congratulations, Dr. Khanna. And it's now my honor to introduce this university's 12th president as of August of this year. Dr. Mark Parlange is a highly accomplished environmental engineer with an impressive scholarly record in several disciplines that bear on the study of climate change and its varied impacts on both cities and remote communities. Dr. Parlange has served for many years as a professor, as a mentor, as a role model for many students, many aspiring academics, all while holding several very important leadership posts at some of this world's top universities. Most recently, President Parlange has served as the provost of Monash University in Melbourne, Australia, one of the top-ranked universities in the world. We are fortunate to have President Parlange join us at the University of Rhode Island. Please welcome him now.
Good morning, everyone. Welcome. And as Professor Snyder just said, there are plenty of seats in the front, and so it would be great to have everybody come forward. Thanks. Look, I just want to also extend my warm welcome to all of you. I'm really pleased that you're here in Kingston, but also virtually. This is an important meeting. It's an important time in the advancement of scientific computing. And so obviously to pull a conference together like this takes the work of many, many individuals. And I'd I'm not going to be able to acknowledge all of you, but I would like to just begin by acknowledging Professor Khan, who we just heard from, Physics Department Chair, long-term member of the community, for his incredible efforts, and those of the organizing committee. Vanita Srinivasa, I would also like to thank you as Program Director, and Gaurav Khanna, Bravo, ITS Director of Research Computing and Professor of Physics. I'd also like to acknowledge and thank all our corporate sponsors, IBM, D-Wave, and Zapata. And I would like to also acknowledge Christopher Savoy, CEO and founder of Zapata Computing. Christopher is a well-known scholar in medicine and biochemistry, along with computer science. And Chris was the inventor of a natural language interface that became the basis for Apple's Siri. He has pioneered the application of big data and bioinformatics to genetics to discover new drugs. He is also a Rhode, true friend, and his knowledge and stature in quantum computing were critical in organizing this conference. And he's been the spark behind our new master's program in quantum computing, one of the first in the country. I'd also like, it was a pleasure last night to be able to meet Jake Taylor, and I really want to thank him for his talk this morning. As you know, Jake is a fellow of NIST, where he runs a research group focusing on theoretical quantum optics, condensed matter, and quantum information. And he was also the first director of the National Quantum Coordination Office in the White House of Science and Technology. And his work there helped pass and enact the National Quantum Initiative Act. So thank you, Jake, for being with us today. Obviously, conferences like this are vital and central to our work as a public research university. And I'm really delighted to also see our friends from Australia and from Canada here. I think it was some 7 years ago, I had my first visit at D-Wave in Vancouver. There's a lot to be talked about in terms of quantum computing, but certainly higher education plays a critical role, both in the education of the quantum workforce, and actually also in the retraining or the re-education of colleagues who have been working in other areas broadly defined of engineering, physics. The MS degree in quantum computing certainly builds on our physics department's strengths in quantum information science, optics, and nanophysics. Look, this work is interdisciplinary by definition. And so when we think for the future, for the algorithms, for the software, for the hardware, obviously we're connecting mathematics, computer science, chemistry, physics, engineering. We have to pay a special attention to the fact that all our efforts must be inclusive so that no groups are left behind. It's also important our partnering with industrial firms, the national labs, and other universities to ensure that our graduates meet industry needs. Obviously, the advances in quantum computing are going to profoundly change the way we think about computers and science in general. And so we're at the frontier of some very exciting possibilities. So I'm also very pleased to be joined today by our United States Senator Jack Reed. Senator Reed has been unwavering in his support for URI for decades, securing critical federal funding for many of our major priorities. I just highlight that he was central to our efforts to secure our new oceanographic research vessel, the Narragansett Dawn. And he also brought federal funds last year to help establish the Train the Trainer program through URI's cooperative extension to reduce food waste and to provide healthy food to underserved populations. Senator Reed has been instrumental in making Rhode Island's universities eligible to compete for EPSCoR and IDEA funds at the National Science Foundation, National Institutes of Health, the EPA, NASA, and the Departments of Agriculture, Defense, and Energy. And so obviously, many of our colleagues across the state of Rhode Island have benefited from his work. He's a senior member of the Appropriations Committee, our 46th senator, and he's widely regarded for his sharp intellect and deep commitment to advancing national security and economic competitiveness. He's been a relentless advocate for his home state, and I certainly appreciate his efforts on behalf of his state's flagship land-grant research university. And so it's for me a distinct pleasure and honor now to welcome Senator Jack Reed.
Good morning, and I am extraordinarily impressed, as I always am, with the University of Rhode Island, with the ability of the university to move forward and to aggressively go, as William Shatner would say, where no others have gone. And this Frontiers in Quantum Computing Conference is an example of that. It's a pleasure to have the opportunity to speak with you today at, as the president said, Rhode Island's flagship public research university. And I want to especially thank the newly installed interim provost Laura Boves, the dean of the College of Arts and Sciences, Jeanette Riley, and the director of the quantum program, Professor Vanita Srinivasa, for their leadership. Thank you very much. In our national pursuit of innovation, quantum information sciences promise to be the next paradigm shifting idea. Pushing past the current limits set by classical computing, communication, sensing, and measurement has the potential for unparalleled scientific and technological advances. Much like when the transistor and the semiconductor discoveries were made at the dawn of the computer age, we're in the cusp of a revolution beyond imagination. Initiatives like the University of Rhode Island's Quantum Information Service Program are at the forefront of this endeavor. By exploring the properties of quantum systems, researchers here will reveal fundamental principles of the physical world, expanding the horizon of human knowledge. As the global community advances quantum innovation, it is vital that our academic institutions lead the world in research and development. URI's initiative will help establish a new hub for quantum information science in the Northeast and provide new opportunities for collaboration and groundbreaking discoveries. In order to maintain our strong research base, the federal government must continue to invest in university research and other programs that support the transition of technologies into commercialization. This means maintaining support for the National Science Foundation, for NIST, NASA, and the research programs of the Departments of Defense and Energy. As demonstrated by breakthroughs ranging from vaccine developments to GPS and the internet, America has benefited enormously from relatively small but stable investments in R&D, research infrastructure, coupled with the entrepreneurial spirit of the nation. And in this moment of strategic competition with other countries in technical fields like quantum information science, we must make sure we remember why investments in science are so critical. Education programs such as Rhode Island's new 5-year bachelor's and master's degree in quantum computing will provide students a gateway to quantum information science right out of high school, cultivating the next generation of scientists and innovators. To meet growing challenges and ensure that opportunities are shared by all, we must continue to attract, train, and empower talented individuals while expanding the diversity of our students and workforce. I hope we can also find ways to expand these educational opportunities to the K-12 level and look for ways to introduce quantum science to transitioning veterans and military dependents like the children of our sailors and Coast Guardsmen in Newport. This also includes welcoming talented foreign national students to work in these emerging fields. America has a major advantage in this aspect, given people's desire around the world to come to the United States to attend our schools, build their careers, and raise their families. Nonetheless, other competitor nations seek to attract the same talent in the same fields, particularly quantum computing and AI. We should do everything we can to continue to be the country where the most technically talented people are welcomed and where they can contribute to growing our economy and protecting our national security. In addition to funding academic and educational endeavors, supporting the private sector will turn theoretical concepts into technological realities while growing the marketplace for quantum industries. As the marketplace expands, it will be critical to upgrade our infrastructure to supply suitable materials and instrumentation. As with our other great technological advantages, the best path forward is a coordinated effort between government, industry, and academia. Both the public research community and private industry have found that the great rewards of quantum technologies come with significant challenges in development. To overcome this obstacle, federal funding is needed to support research and development at every stage. Great progress is made through programs like the Defense Quantum Information Science and Technology Research and Development Program and the National Quantum Initiative. Efforts like these should be leveraged to continue to cultivate early and ongoing support. Importantly, quantum information science will lead to revolutionary new capabilities for our military. The potential applications are far-reaching to include improving our ability to sense enemy threats, breaking adversary encryption, supporting unhackable communications for our forces, and improving the precision of our navigation systems and munitions. Federal support for quantum innovation endeavors will both ensure U.S. leadership in the field and secure our place in the quantum economy. And as the chairman of the Senate Armed Services Committee, I'm proud that the fiscal year 2022 National Defense Authorization Act authorizes the program to accelerate quantum computing capabilities. The bill also authorizes significant funding for DARPA's research on quantum information sciences and lends broad support to the DoD's efforts in these areas. I look forward to working to ensure that this funding is included in the final appropriation bills. As we have seen in other global transitions, including pandemics and armed conflicts, the first nation to achieve preeminence in a paradigm-shifting technology reaps enormous scientific, economic, and military advantages. Therefore, in addition to the continuing support of fundamental research in quantum sciences, infrastructure, and education programs, the United States government should develop plans to be the best positioned nation in the world in quantum computing. Formalizing a coordinated effort between government, academia, and industry that strives to move technologies expeditiously from research to commercialization and operation will be critical to achieving this goal. I again want to applaud the University of Rhode Island for taking a great stride forward in this endeavor and for convening this important event. I look forward to following the program's research and hearing from the participants of today's conference. Thank you, and for a job well done on the leading edge of the technology that we want to be first in, because second place would be, think, very uncomfortable. Thank you very, very much.
So thank you very much, Senator Reed, for being here and for those wonderful remarks. So we're going to continue on with the second session of the conference, and that is Quantum Education 1. So I'd like to ask Jake Taylor, who's the chair of the session.
All right. Well, Chandrasekhar, you've got your set. Great. Well, so that's, of course, some tremendous remarks from Senator Reed. Thank you so much, Senator, for those. And I'm thrilled to have Chandrasekhar Singh from University of Pittsburgh, who's been doing, no one can hear me, of course. Right. Who's been doing some education, particularly quantum education, and not quantum education for graduate students, but quantum education going all the way in to the middle school, elementary school, and high school levels. This is an extremely important area and an extremely challenging area. So really look forward to hearing more about it.